Implementing behaviors is always the easy part of software development. When we add performance targets for these behaviors into the mix, and that's when solutions become complicated. There are already solutions curated and tools made, but the tough part is knowing about them and when to apply them. That's why I will show you in this video how to approach designing software applications for performance using the most basic systems design building blocks. The low-hanging fruits that will give you a head start. This will give you a basic but sound systems foundation for further enhancements and improvements. My name is Derick Chen, and this is Build with DC. So what's the difference between behavior design and performance design? Behavior is what the system should do, and performance is how well it does it. Let's take the example of Google search. The behavior requirement is pretty simple. I should be able to enter a search query and get 10 URL links. The performance requirement for this behavior can include but not limited to 1. The speed for the results to show up, and 2. How relevant the top links are. Behavior is what the software should do, and performance is how well it does it. The goal of performance design is typically to deliver an improved user experience, which in turn should lead to higher customer lifetime value. Performance design plays a critical part in managing the 4 constant challenges for software systems, especially for the changing usage level, technology, and integration. I have explained these challenges in greater detail in the video linked to the top of the screen right here. Once we tackle these challenges through performance design, we can achieve better adaptability for our software system. At the user-facing application level, we can break down performance in 3 key areas: response time, throughput, and scalability. Of course, there's more to performance than just that, such as reliability, security, cost, and more. But since we're designing software solutions, we will first tackle the user-facing performance requirements for the application. It's a lot. I know. That's why we don't try to predict performance requirement a year down the line and build super robust systems for just MVP projects. Performance design needs to be incremental and properly owned by the technical team iteratively, without elaborate upfront design. A common problem is our lack of knowledge for solutions and tools available to tackle performance issues out there. There are many types of systems design building blocks, and of course even more software solution vendors who implement this with a conscious trade-off. That's why I built a simple and free knowledge topology map called Systems Atlas. The major classes of system solutions are organized by challenges they solve, so you no longer have to look for the needle in the haystack. The starting point is the performance requirement that you want to address, and it shows you the relevant solution categories and of course specific tools available with details and considerations. This helps you narrow down the sea of options out there, evaluate the trade-offs, and also apply them to your project. I will leave the link in the description for you to explore more. But in today's video, we're going for the low-hanging fruits for performance design, namely the direct deployment options for our services from behavior design that can help us improve the performance of the system. Then, in the second part of performance design, we will discuss some more sophisticated design patterns to meet more stringent performance requirements at scale. So let's get back to my café scenario. Once we have the result of behavior design, we know the services we need to implement and also the corresponding responsibilities. We need to implement 3 services in our simple café: the order service, the payment service, and of course the fulfillment service. The choice of programming language here does not matter too much at this point, but I will generally recommend a strongly typed language with good OOP features. We will focus a little more on the infrastructural deployment options here, because there is a lot of performance to be gained in this layer without major changes to the application code. There are 3 decisions that you will always make every time in every service. The deployment choice for the integration blocks, compute blocks, and persistence blocks. Let me explain. Firstly, integration refers to how we manage incoming commands or triggers a new transaction in the service. We need to expose a surface of every service to allow other services and also clients to initiate workflows. There are many ways you can do this, such as a REST API or an event queue. These solutions typically don't persist any data to disk for better performance, but acts as a buffer zone and abstract the inner workings of each service. With REST API, the URI naming, structure, and definition allows particular workflows of the underlying service to be initiated with relevant data in the payload. In an event-driven system, there is usually an agreed-upon event definition where other services could put the workflow requests with the relevant data in a single item into the queue. It is of course possible to have a hybrid solution where we place a queue behind a REST API endpoint to manage spiky and irregular traffic and make sure that we don't lose any important data and requests. In our café, both options are equally viable. Secondly, once we receive these workflow initiation requests, we need to process business logic using compute blocks. Hence, the compute blocks refer to application hosting options that enables the processing of business rules and data. This is where your application will live. There are three broad categories of options here: the good old VM-based hosting, containers, and finally function as a service. These three categories have decreasing degree of operational overhead in the order that listed them, but also typically finer and smaller units of deployment. In a good VM-based hosting option, you manage the service lifecycles and security patching and all that. In exchange, you are closer to the metal and have fewer restrictions of what you can and cannot do. On the other hand, function as a service, the deployment unit is typically much smaller as it can be scaled up and down significantly quicker than VMs and containers. The trade-off here is that it is typically more expensive and usually has some limitations of the size of the package you can deploy to. Containers is in the middle. It strives for a good balance among the trade-offs, but you may need additional knowledge and management overheads for the container orchestration, such as the Kubernetes. It may not be a worthwhile time investment depending on your scenario. For modern applications, it is quite rare to have a fully VM-based deployment these days due to high operational overhead. Containers are a good option for predictable traffic patterns with lower costs. Otherwise, if you're dealing with spiky and unpredictable traffic, then function as a service is the way to go. With an understanding of the business transaction patterns, you can make an informed choice for the compute deployment. Okay, so which option should we use to deploy our café's order service? Since the demand for coffee is relatively regular, containers with scheduled scaling events will be a good option. But our café is really unique and we're hoping for it to go viral and make it big, attracting thousands of people ordering deliveries possibly at any point in time. Then we need to deploy it as a function as a service, where scaling is much more efficient. Thirdly, we always have to store some data to disk with the outcome of transactions so they can be referenced again. We can use a database. There are different types of databases, and I will get to that in a minute. Or we can use a file storage option. Most business transactions result in serialized data that can be easily modeled and stored in databases. Generally speaking, there are three categories of databases: relational, document, and graph databases. The choice of the database category depends on the nature of the data. If the data is discrete in nature, for example, to store the name, email address, and birth date for a particular user, then a document database should suffice. But if there is a strong tabular structure to the data, then our good old relational databases would be the best. Otherwise, if the relationship between data points are dynamic and complex, then it's time to consider a graph database. These are commonly used for social networking use cases. Relational databases mostly use variants of SQL, while graph databases typically have non-standardized query language depending on the implementation and provider. So do keep that in mind. You might need to learn a new query language, but usually they're not too difficult. When you are persisting relational data, it is important to understand your choice of database and to model your data correctly to achieve higher read and write performance. In the cases where the transaction results in the production of a large object that cannot be serialized effectively, then it should be persisted as a file or an object of its own. An example would be an image enhancement service where it takes in a raw image for enhancement and returns the output image. It's a little bit silly to try to fit that into a database. So back to our café, to store customer information in the order service, we just need a simple document database. The simple customer profile data with names and birth dates has no relational requirements. But when we implement our fulfillment service for order deliveries, where we need to keep track of delivery drivers and orders being delivered, a relational database will make more sense. Of course, there are other important performance solutions that I'm not covering in today's video. For example, caching and CDNs. Our discussion today should give you a fundamentally sound, basic deployment option to host and operate the application services. I will leave it to you to explore the other commercially available tools and solutions. Again, if you want to quickly shortlist tools that can help you to solve a particular performance challenge, check out the free Systems Atlas in the description. These are the most basic tools and solutions that are available for systems design. They are mostly easy to integrate with and can help us improve the performance of our applications to an extent. As your application becomes more complex and performance requirements become harder to meet with the increase in traffic, then we need to explore more sophisticated options. In the next video, I will show you how to combine these basic blocks of systems design in patterns that help us push the performance limits of distributed systems. So when you're ready, check out the second part of performance design right here. My name is Derick Chen. Thanks for watching and see you in the next video.